Hi, welcome back to topic on modern manufacturing methods. This modern manufacturing methods is developed based upon the drawbacks of or limitations of conventional manufacturing methods such as casting and conventional manufacturing machining processes and many more. So the limitation of the particular manufacturing processes, it is mainly because of delay in production process or time, and customer require sometimes very fast products. So during such cases, so these manufacturing techniques, conventional manufacturing techniques are lagging. So to improve that part, so rapid prototyping manufacturing methods are emerged. So these manufacturing methods we'll discuss in coming slide. So we'll start with small activity. You choose any paper and make it into fold. And finally, if you want to make a shape, generally we try to start with a square shape from rectangle, and we try to remove one of the part, or we cut the parts which is not required, and we try to mold and folds different manner. Finally, we achieve the product. So during this building of this toy or paper based type model ship, we try to remove the material from one shape to another shape. So what we are understanding here, so we are removing materials. It means we are wasting some materials to achieve a particular shape. So that's we generally technically we call subtractive manufacturing, subtraction of some materials to achieve the final. So to minimize those, so 3D printing technologies emerged. These are generally applications. Instead of subtracting the material, we started to do addition of material from one layer to another layer. Like these layers are formed based upon the drawings which we will give through CAD model. So these CAD models generally designed through uh, any particular software, CAD software, and these CAD model softwares. Right, finally we started to give slice, and during the slicing we generally follow some certain operations to build the material without any defects of final product. So most common industries for recently each 3D printing applications. Now we can understand medical devices are developing like 73 percentage, and consumer electronics for 52 percentage of production parts. We are still relying on 3D printing. And for automotive applications like bridge productions, 39 percentage some parts. And for transportation, for repairing and maintenance parts, we are relying on 38 percentage. And medical devices, we are using for fixing the tools for 37 percentage. Currently, for many applications, so this kind of uh, 3D printing uh, we are using for different applications, even for kids' toys, and to show any uh, educational purpose, some objects we are printing 3D models. And for medical applications, before making any surgery, the doctors can understand like human body nature of particular patient, so that he can easily can perform the operation. Not only that, it also useful in food industries such as, especially for chocolate makings, printing, and cake 3D printers, 3D printing, and so on. Then what is model? The model is a non-working a representation used to illustrate the product. But the prototype is a working representation used to detect flaws or problems in advanced production. So in prototype, mainly we can observe the actual working representation, whereas compared to the model, which is used to detect flaws in or problems in advanced production. So earlier stage itself, we can detect some of the issues which is having uh, before releasing any product. This is generally applicable to any product based or software based content. So what is this fabrication? Generally, as I told you, this there are different kinds of fabrication processes. Whether when you remove the material from the raw material to make any final product, so we do different form of operations, especially this kind of shape. To achieve this shape, we initially take one block and we try to remove this material by doing different operations, maybe a milling operation. So, so that this material can be a scrap sometime. Additive manufacturing stage, we do addition of the material layer by layer to attain its required position. In formative layer, mechanical forces are applied on the material so to form into the desired shape. Especially, you take a block and we make different form of formative dies. So when we apply mechanically force on the both side, so this part get achieved required shapes. This is the three different kinds of fabrication process generally. And definition of rapid prototype manufacturing. So use of computer-aided design (CAD) based upon automated additive manufacturing process to construct parts that are used directly as finished products and components. According to ASTM, it consists now use the term additive manufacturing. So introduction of this AM process, which is a digital 3D design data, which is used to build a component and layers by depositing the material. The term AM represents composites by many technologies, including 3D printing, rapid typing, direct digital manufacturing, layered manufacturing, and additive fabrication. So, additive manufacturing applications is limitless. It starts from a school kid toy, from any small toys to large scale rocket fabrication. Everything is possible through this additive manufacturing process with various kinds of technologies under AM. So more recently, AM is being used to fabricate end-use products in aircraft. So not only the production side in factories, this is also placing major role under dental restorations like metal-based tips on any jaw dislocations happen due to any accidents. So that part can be replaced through this AM process by doing scanning of MRI of the particular patient and then apply those replica of the MRI scans to the uh, mimic the exact dimensions and through this mimic software, then that can be printed through uh, one of the CAD, one of the additive manufacturing process. So that will be a SLS. Another application is like medical implants, where the medical uh, parts are being manufactured through additive manufacturing process, maybe SLM or SLS, and also automobiles applications and any sub-assembly part of the automobile component got broken. In such cases, these automobiles parts immediately can be manufactured through rapid prototyping process, especially when the components got stopped during service life of that maybe or some companies cannot produce again old based products designs. Such cases, the old design can be scanned through laser scanners. So the scanning images we form give the CAD models. So this CAD model will do slicing, and after that we go for 3D printing layer by layer. So even for fashion products and even for architectural displays, they are using additive manufacturing technology. So that comes under LOM. LOM is one of the important technology comes under additive manufacturing. When the client wants to see the additive manufacturing, any uh, building architecture in prior to the building construction, they can easily can see the prototype model in through LOM process. Additive manufacturing process chain. So here it generally focuses additive manufacturing in different steps. First one is conceptualization and CAD design. So through this, we can easily make uh, design and optimized design can be drafted through CAD model. So later, the CAD model directly cannot able to feed into the systems to the 3D printer. So this can be converted, has to be converted into convert STL file. So this STL file, which is generally saved when you're after designing. So after that, we convert it into G code. That G codes of this particular through STL directly transfer to the additive manufacturing machine. That may be a future deposition machine or SLA machine or direct energy depositions or SLS, selective laser sintering or selective laser manufacturing. For every AM process, so this is a common phenomena. Sometimes this post processing is not required, but and this is not required some cases, but remaining all is common for all this kind of 3D printing techniques. So once the G codes in is transferred to the additive manufacturing machine, so machine setup is very much important. So where we have to consider the preheating. So where the material is going to build, example, this is a machine, and where this is the platform. The object is going to build on the surface. So if we don't preheat, the material will not able to stick properly to the surface. So this is a disadvantage, and this will affect on complete body surface in later stages. So that's the reason every aim process generally they started to do preheat. So for example, FDM they heat up to certain like 3 to 60 degrees centigrade. So once it is preheated, the ABS material or PLA will started to form layer by layer with the proper manner. Then once it is properly fixed the parameters, then we have to start to print that particular model. And this is started to build according to the dimensions which we gave, and based upon the intricate shape, it started to build. For example, if you want to build such kind of hollow based structure where the length is very high and which is not come to the print of this build area. So due to such cases, we put the inclination, but we put some support so that it will get able to print in that particular area. So later stage, this can be removed by post processing. So this kind of arrangement and analysis can be done in the uh, stage of build area, build stage. So once it is got printed, so we can remove this or we can clean up the supports and especially for FDM. And after that, we go for some grinding or smoothing operations to attain a good surface finish. Later, in some stages like this kind of SLA or another uh, kind of DED or models, where the material is not able to uh, no need to do this shearing operations. Simply we dip into some alcohol based liquid so that the supports can be easily removed and we can achieve the smooth surface of objects, especially this kind of applications like jewelry applications and surgical operation sub parts can be where the surface finish is very much required. Intricate shapes with lesser volume objects can be printed in SL emissions. Later, post processing, then based upon the application, we can use. So, as I discussed, so this is the one form of for 3D for rapid manufacturing process chair. So, where you started to design CAD model, then STL conversion, then file transfer to the machines that may be any machine, FDM or additive manufacturing based or 3D printing based machines. Once it transferred to the machines, then we have to keep the setup of that particular machine. As I told, this preheating and remaining operations. And once it started to print, then it started to build. Once it is get built, then we have to remove in case any supports or it is attained to that can be removed. Then later we can go for post processing where the excess amount of material stick to this surfaces or any supports are there, you can easily remove. So after post processing, we can see the final form of object for the particular applications. So So this is the general process chain of AM. There are various technologies under AM, additive manufacturing, but common use uh, 3D printing technology or prototyping technologies or here FDM, future deposition modeling. Here, generally can go for polymer based objects. You want to print that can be printed by layer, where there is a spool, the ABS or PLA or some other polymer based material will started to come through a nozzle which is having maintaining some temperature that is 200 to 220 degrees centigrade. So under this spool will get float and it will started to build layer by layer according to the CAD design. So with this, we can able to print only plastic based, but polymer based. But the problem is the surface finish is comparatively uh, another technology like SLA. This is very poor, but we can achieve this 3D printing from this any model very faster way. So whereas in SLA, select stereolithography, where the build area is completely get submerged in the resin. So this photopolymer resin will react with the UV light, which is project from that below. So this body or the platform is fixed to the lead screw, and as the UV light is getting projected on this bed, so this layer will get formed, and accordingly the object got print in this bed. So since it is preheated, the material is get properly stick to this surface. As soon as the material get built, so this part will go up. So this is anti-gravitational ob- object printing we can see here. Whereas here the object is print on the surface and it will build layer by layer from bottom to top. Whereas here, so we can see the print layer bottom to top to bottom. But however, the you can see the replica of this after removing the object. So after that, another technology SLS. So where you cannot achieve with these two for large components, we can achieve in certain kind of print technologies through SLS, where the powder bed will be there, three chambers, and there is a sweeper. So it's filled with completely the required material which is required for print. So as a laser will project complete on the surface. So before that, the material get moved from left to right because of this spool, and it will form a layer on the surface. After that, so it will get immediately fuse. So due to this fusion, the one layer get formed. So after that, the excess immovable material will get removed and stored in another uh, chamber. So as soon as the material get print like this, so this piston will go down, so we can find entire object here. Laminated object manufacturing. So this is generally want to build any prototype in the large scale architecture models with the highly intricate shapes. We can be able to show the client. In that situations, we can easily make layer by layer printing of that particular designs of there. So later, direct metal laser sintering (DMLS), we can use this kind of operations manufacturing process for any large scale aerospace applications. We'll see briefly about this FDM. As I discussed, so this is a 3D printer of FDM machine with deposition modeling. So this is the extruder and jet motor. So when the material is moving and getting built, so this Z axis will move upward direction. So where we have pulleys, these pulleys generally will guide this X directions, and Y motor will allow the motors this nozzle to give the guidance to Y directions, and the main board will have the power control everything. The X motor will allow us to move the object in X directions. The hot bed generally is required to stick the initial layers of um, printed parts. Then fixed plate. So this fixed plate generally it is uh, fixed with the below of the base. So on this generally hot bed will be clamped. So once it is get print, generally hot bed will remove white layer and we'll use that sharp edge knife to remove the uh, build part from the bed area. The next one is nozzle. The nozzle will allow us to 3D printer give the particular directions which is required for printing. Then heating block allow this materials to melt at 220 degrees centigrade approximately. So the temperature which is generating through the nozzle at the nozzle easily can be get cooled by using motor fan. So all these operations, initial preheating setup and initial stage setups can be uh, give the inputs through this knob where you can have all the parameters can be adjusted through this by seeing the screen. The microscopic view of this nozzle where the filament material is passes through the spool and the pinch rollers will feed the system by rotating in different directions of the spool. The material filament passes through liquefied chamber and entering to the nozzle. So this is very important. So the nozzle diameter vary in different sizes, 1.5 mm to 0.5 mm to 2 mm. So as the material diameter is nozzle diameter increases, it allows more materials to print on the surface. So this scaffold will be the uh, already printed layers on the platforms. So X and Y directions will get moved. So as the material is getting built, so this part will, this complete part will go upward direction. That is their direction. So FDM material type generally we use filaments, solid materials like ABS, polycarbonate, polyurethane fluoride, polypropylene sulfonate also can be used, and also use elastomers. Minimum layer thickness to 5 mm we can achieve, but surface finish is very, very poor in this case. Build speed is very slow in such cases. SLA allows materials to print, as I discussed. In SLA operations, where we have the lead screw, you can see, and to that there is a platform, and this is the resin which is completely filled with the container. In the container, as I told, sometimes the laser will project from the top, sometimes in the bottom. Some of the companies like Home Labs, this laser will project from the bottom through the resin, so where the material or required part get built here. In some other SLA based 3D printers, so they have laser projection system on the top. So in such cases, so the print can be built from the top of the um, bed. However, in both the cases, so material is getting photopolymerized inside the surface, liquid resins. So material generally we use photopolymer, and materials generally thermoplastics applications and zero point zero 0.02 micro mm, right? In 0.02 mm, we can go up to the particular thickness, and highly smooth surface finish we can achieve with this. Build speed is average compared to um, FDM. FDM having very faster prints. Application like any fit testing or forms can be print through this. Functional testing can be done with this. Detailed parts like jewelry applications or any dental prototype models can be easily can print, and any presentation models can also be print. After SLA with another technology that is SLS based, so that also powder fusion process where the material gets fused. You can see here they discussed in the second slide. So this is the bed where the counter rotating powder leveling roller will rotate on this from left to right, right to left. So under the cases, the CO2 laser will come through this source, and X-ray scans will project according to the directions which we gave in CAD model, and it will get print with this dimensions. So after that, the bed will go down at the required amount of thickness, which is printed. So the same thickness will be immediately moved towards downward direction and ready for the next printing operations. So if you see the microscopic view of this, so there's a transmitted layer will passes through laser, which is not getting cured of the sintered without sintered areas. The unbound powder will be the another side. So this will be removed after the one layer of print, both the sides. And this is only the sintered area. So the excess amount of laser will get radiate from the surface of the objects. So powder generally we use for this polymer based materials, thermoplastic, nylon, polyamide and polyestyrene, elastomers, and composites. Up to 1 mm, 0.1 mm, we can able to print the thickness. Average surface finish can be achieved. And build area is so mainly the applications which we can see like functional testing and less detailed parts can be printed through this, and high heat applications also can be used. So LOM is another important applications where architectural prints buildings can be want to show in under prototype model where we can print in this chamber where the supply of roll will passes through this way and required dimensions of a particular prototype building model can be designed and fed into this CAD model. This laser will guide and it will started to give cure particular the shape of CAD model. So as soon as it's get cured, then the excess amount of material will get removed and the remaining part will roll and it will get stacked here. So this is a very important for especially architecture based applications where the material can be used here for the sheets, PVC, papers, and up to 0.05 mm resolution thickness we can achieve, and but the surface is very high, but the build speed is very fast. So where the rapid tooling parts are required and architectural prototypes can be print. DMLS is similar kind of technology where laser sintering will be only for polymer based. So another technology, laser metal uh, melting also. So there material get melted instead of fusing. So the difference is the use any two kind of similar any materials to want to bond. This powder can be fused with an additive and apply at not up to melting point temperature. Then it will get started to fuse and it will get bond at a unit cell. So whereas in melting stage, the complete powder will get melt and deform its shape and it will get it, its unique shapes by getting melting of powder particles. So most of the times they use here metal based. That is reason we call this selective laser melting process. In both the cases, the limitation is limited area we can able to print the object either polymer based. Using SLS, it is metal based. Powder-based is metals, selective laser melting, ferrous metals such as steels, alloys, stainless steel, tool steels, bronze, aluminum, and various kinds of advanced materials like titanium, cobalt, chromium, ceramics can be used. Up to 0.02 mm we can achieve. Build area, build we can very faster way. For rapid tooling and high heat application, we can go for this selective laser melting operations, especially for aerospace applications. We easily use this kind of application. Apart from this, another technology which is direct metal deposition, DMD. So where the plasma are will started to come print by using a passage of material through a setup of nozzle like this. Material will enter the laser high energy beam will project on this particular area and shielding to avoid any oxidation of it. There is another gases will support so that can able to print layer by layer into very large area components. This is the advantage of uh, direct deposition uh, printing. Thank you.